All right, let's get right into it. If you've ever been prepping for a coding interview, you know the feeling, right? The pressure is on. And it's not just about writing code that actually works, it's about writing code that's good. But what does good even mean? Seriously, how do you measure it? If you have two different solutions and they both give the right answer, how do you decide which one's better? Is it the one that runs faster? The one that uses less memory? This is the question every developer has to answer, especially when that interview clock is ticking. Now, your first instinct might be to just time it, right? But hang on. Let's say you run the exact same code on my old clunker of a PC and it takes 2 seconds. Then you run it on a brand new laptop and it takes 1 second. So is your code 2 seconds fast or 1 second fast? It totally depends on the machine, which makes it a pretty useless measurement. Yeah, because timing your code in seconds is so unreliable, we need a universal standard. We need a way to talk about how efficient our code is that doesn't change whether you're on a supercomputer or a 10-year-old desktop. And this brings us to our first big idea. We're going to figure out how to judge code performance without even looking at a clock. We're moving beyond just raw speed to something way more fundamental. And that universal standard is called time complexity. Now, this is a really key shift in thinking. We're not measuring absolute time in seconds. We are measuring the rate of growth. In other words, we want to know how the runtime of our code changes as the amount of data we throw at it gets bigger and bigger and bigger. And that's really the heart of it all. See, nobody really cares if your code can sort 10 items. That's easy. The real question is, what happens when it has to sort 10 times million items? If you're building a social media feed or a search engine, you have to know, does my code scale gracefully or does it just grind to a halt? That's the real test. So this is the question you should always be asking yourself. If I double the size of my input, does the amount of work my code has to do also double? Or maybe does it quadruple? Or in a really bad scenario, does it just explode? Answering that is the essence of performance analysis. So to have this conversation properly, we need a common language, right? We need a standardized notation that everyone in the tech world uses to describe this rate of growth. And that language is Big O notation. You've probably heard of it. This is the industry standard. It's what you'll use in interviews, on the job, everywhere, to talk about how efficient your code is. It's how we put a precise, simple label on that growth rate we were just talking about. And here's the best part. You hear the word notation, and you might think it's going to be some scary, complex math. It's not. Calculating Big O really just boils down to following 3 simple, powerful rules. Let's break them down right now. Okay, rule number 1. Always analyze the worst-case scenario. Sure, your algorithm might get lucky and finish on the first try. That's the best case. But we don't really care about getting lucky. We're interested in the longest possible time it could take. We plan for the hurricane, not the sunny day, because we need our systems to be reliable even under the absolute heaviest load. Rule number 2. Ignore the constants. This one's pretty intuitive. Think of it like this. If you're earning $1 million and I walk up and give you $1 single, is that going to change your life? No way. It's insignificant. And that's exactly why we don't consider constants. When your input n is massive, a small multiplier in front of it just doesn't change the big picture. So in Big O, we just drop it. And rule number 3 follows the same logic. We drop the lower value or non-dominant terms. If your total operations look something like 4n cubed plus 3n squared plus 8, just imagine n being a huge number. That 4n cubed term is like a rocket ship. The other terms, 3n squared and 8, they're like paper airplanes trying to keep up. They get completely overshadowed. We only care about the fastest growing term, the rocket ship. So we simplify that whole big expression down to just on cube. Okay, so we've got our rules. Theory time is over. Now for the fun part. Let's see how this all works with some actual code. Take a look at this. This is a classic nested loop. You'll see this everywhere. The outer loop runs n times. Simple enough. And here's the key. For each and every one of those n times, the inner loop also runs n times. So the total number of operations is n times n. That gives us a time complexity of O of n squared. See? Easy. Now here's one that's a little bit trickier. The inner loop here runs up to I. So it runs once, then twice, then 3 times, all the way up to n. Now, if you remember from math class, the formula for that sum is n times n plus 1, all divided by 2. If you expand that out, you get n squared plus n divided by 2. Now what do? We just apply our rules. We drop the constant, so go by division by 2. Then we drop the non-dominant term, see you later n. And what are we left with? You guessed it, still O and n squared. So, we've covered time pretty well, but that's really only half the story. Efficient code isn't just fast, it's also careful about how much memory it uses. So let's talk about space. And this is called space complexity. It's just a measure of how much memory your algorithm needs to do its job. That includes the space for the original input, plus any extra memory you might create along the way. We call that auxiliary space. For example, if you make a full copy of an input array of size n, your auxiliary space complexity is O of n. And the best part? We measure it using the exact same big O rules we just learned for time. No new rules to memorize. Now, here is a crucial piece of pro advice for any interview. It can be super tempting to save memory by just modifying the original input data. My advice? Don't do it. In a real-world system, some other part of the program might still need that original data. Changing it is just bad practice and can create some really nasty bugs. It is always better to use a little extra space and explain to your interviewer why you're making that safer, professional choice. They'll appreciate it, trust me. Okay, so we've got all this theory about big O for time and for space. But you might be wondering, how does this actually connect to the real world of passing a time to coding challenge? Well, this is where a fantastic rule of thumb comes in to tie it all together.
I want you to remember this number, 10 to the power of 8. That's a 1 followed by 8 zeros, 100 million. This number is the magic key that bridges the gap between abstract theory and passing your tests.
Why? Because 100 million is roughly the number of operations a typical server on a platform like LeetCode or HackerRank can perform in about 1 second. So think about it. If the input size n is 100,000, an O of n algorithm is totally fine. That's only 100,000 operations. But an O of n squared algorithm? Whoa, that would try to do 10 billion operations. There is no way that will finish in 1 second. You'll get that time limit exceeded error. Suddenly, Big O isn't just theory. It's a practical tool you can use to predict whether your code is going to pass.
So there you have it. We went from this vague idea of good code to a concrete, universal language to measure it. With the rules of Big O and the 1 second rule in your back pocket, you're not just writing code anymore. You're engineering efficient solutions. So the only question left is, how are you going to analyze your next piece of code?